Did you know that juggling involves mathematics? For example, Claude Shannon, who invented information theory, was a juggler, and he derived an equation relating the number of balls, the number of hands, and the length of time the balls are in the air or the hands. But that's not the math I mean. There's also math in the parabola shape that balls make as they fly through the air. A juggler needs to estimate the complete parabola after seeing just part of it to know where to catch one ball when looking at another ball. But parabolas are also not the math I mean. There's also a quadratic relationship between duration and height. If you want a ball to stay in the air 3 times as long, you need to throw it 9 times as high. But that's not the math I mean either. Some of the most interesting math in juggling involves planning to avoid collisions. If you throw one ball high and then another ball not so high, so they both land in the same hand at the same time, then you can't catch them both. Well, most of the time you can't. So a good mathematical puzzle is to think of a sequence of throws so that at each clock tick, exactly one ball lands. If the balls are all thrown the same height, it's easy. With n balls, you throw one ball at each clock tick so they each land n ticks later, one at a time. From above, you can see we alternate left and right hands at the clock ticks. With 4 balls, it's the same idea, but now the balls land in the same hand because n is even. So here is first 3 balls all thrown the same height. Then add 1 to make 4 balls all the same height. And then add 1 more to make 5 balls all the same height. With 5, you can see they cross to the opposite hands, and they go pretty fast. The fun mathematics begins when you try to think of patterns where the throws are not all the same height. The history of juggling goes back thousands of years, but only in the 1980s did people start rigorously studying the possible mathematical patterns. For example, with 3 balls, instead of throwing just 3, 3, 3, 3, 3, you can throw 4, 2, 3, 4, 2, 3, 4, 2, 3. This goes on forever without 2 balls ever landing at the same time. The 2 is a short toss to the same hand, so you can just hold on to that ball. Modern mathematical juggling involves understanding all the possible patterns and seeing which ones you can learn to throw. The 4-4-1 pattern is another 3-ball pattern that works out to have no collisions. People have been juggling at least since the ancient Egyptians, but no one thought of this pattern until the 1980s. And here's the 5-3-1 pattern. It's interesting because there's a point where all 3 balls reach their peak at the same moment. With 4 balls, there are more challenging possibilities. This 5-6-1 pattern takes a lot of concentration. Notice, by the way, that the average of 5, 6, and 1 is 4, the number of balls. There's a lovely theorem that the average of the digits in any juggling pattern is the number of balls needed. For example, we just saw the patterns 4-2-3, 4-4-1, and 5-3-1, which are 3-ball patterns, and they each have average 3. Another is the 5-1 pattern, which also uses 3 balls. The theorem tells us that 7-5-3-1 is a 4-ball pattern. If you look hard, you'll see there's a point where all 4 balls are at the peak of their arcs. Professional jugglers like to challenge themselves with these tricky patterns. So watch for the 2 high throws of the 7-5-7-5-1 sequence. Juggling also has connections to the mathematical theory of braids. If you walk while juggling, the paths of the balls in the air form a braid. We can get the same effect by tying a string to the balls. Here, a simple 3-ball pattern gives a standard 3-strand braid. The 5-1 pattern gives a different 3-strand braid. In this case, it's just a spiral twist, not especially interesting, but technically that counts as a possible braid. However, the 4-2-3 pattern does give a different and interesting type of braid. Braids form what mathematicians call a group. So braids can be combined into larger braids, like addition. There's an identity element, like 0, which is just unbraided strands. And they have inverses, like a negative braid for every braid. This algebra can be transferred to juggling. So it's possible to juggle a long braid, then switch to juggling its inverse, and have them cancel out completely. You end up with the identity element braid, which is just 3 parallel strands. The fact that juggling and braiding have certain underlying structures in common is a nice example of how mathematics is about deeper patterns, not just what's on the surface. And is this useful in everyday life? Why, of course.